home and computer science. And actually, this is the second time I'm giving a talk in this room. The first time was my job interview at Rice. So I'm having some flashbacks. So in case I black out, please forgive me. So since I usually don't speak to this crowd, so I think it's better to give a little background about what we do, who we are. So there's a picture on the left is a grad students, on the right is the undergrads we have been working with. And there are computer science students in there. Can you spot them? Right? And one of them is left, Peter Washington recently joined Stanford, right? We didn't manage to keep them, man. They're mostly in Stanford. So, but this is the people who did all the wonderful work, okay? But most of what we do is building system. We're not theoreticians, or we use theory, but we don't contribute to theory. We mostly build things. And to give you some example of what we built, this is one of the big things we built is a massive MIMO mini antenna base station. This is a base station, serial base station prototype with 100 antennas. You can count how many antennas, right? It's actually 84 in this picture, but in some other configuration we have 100. So this is in the NASA's annotation chamber. We're doing a testing measurement of that. Okay. So if your Wi-Fi doesn't work sometime in Duncan Hall, maybe this is a guy Clay Shepard, not me. Right? We also deal with small systems. That's actually what I talk about today. Phones, wearables, watches these days. Both software system and also look inside the system, like working on hardware, for example, system chip. That's actually what I'm going to talk about today. I was here last week, the week before, so Dan and Chris set the bar really high to give a talk, so I cannot beat them giving a big picture talk, so I decided I'm just take one small project I've been working on in the past year and talk about that project particularly, so that you kind of get to a sense of what our daily life is, what kind of things we're working on. Okay. So the title, I try to be humble, how to save 10 milliwatt for free. Right? I'll give you the answer up front. Is don't trust device drivers, right? And I will give more background, right? This work actually, the student who did the work actually, all of them left. So I'm the only one here who understands this work. The source code is available on our website. If you're interested in the work, you can check the source and play with it, right? So the important thing I'm trying to convince you 10 milliwatt actually important. That's the most important thing to do at first, right? So power matters at a different scale. For the system, for example, like John cares about, they worry about hundreds of watts, tens of watts, right? Data centers are supercomputers. That's where you worry about heat dissipation, electricity bills. And then if you move to like your desktop computer, you worry about several watts of power consumption. That is something you worry about is the heat, thermal management. When you move to laptop, you care about battery lifetime. With a laptop, you care about even 100 milliwatt. Moving to your phone, 10 milliwatt is important because your battery is about 1,500 milliamp hour. Right? And if you move into even smaller factor with form factor with smaller batteries, like a watch, like glasses, like even 1 milliwatt power consumption. Right? So what we'll talk about today is relevant to the last two categories: wearables and mobile devices, phones. So 10 milliwatt does matter. Okay. So the secret of efficiency, this is really important, right? So being an efficient computer system, efficient person, student, professor, is don't do unnecessary things, right? So for example, you do it as slow as possible, right? Don't over prepare something, and don't do useless things, right? And reuse previous work. Don't reuse your text, write up, whatever, right? So, but my favorite is really this one, right? When you don't have anything to do, go to sleep, right? This has a nice name in system called power management. That is, when you have nothing to do, go to sleep, right? This is the best efficiency strategy ever, okay? And then in computer system, people do this at two levels, right? One is called system level, system power management. Like your Android phones, when you press a button to turn off, it's really, you suspend the entire system. The phone is not functional. It wake up by background activity occasionally, but most time it's not doing anything. Everything is suspended, right? there's no service running, except you listen to something, you wake up, for the background activity. But the things I'm going to talk about here today is called runtime power management. That is, even if you're using your phone, you're reading the news, you're checking your email, not every component of the phone is actually doing useful thing. Many of them idle, right? So runtime power management basically puts idle components into a low power mode, into sleep, right? When the rest of the systems you're doing things useful for you, right? The distinction is clear, I hope, right? System power management is push the power button, everything goes to sleep, that's it, right? And runtime power management, you think your phone is working, right? But most of the time, most parts actually sleep. So sometimes I think the undergrads in my class, they're doing runtime power management. Their eyes are open, but their brain perhaps is sleeping, right? So that's a good analogy, I think. So for the rest of the talk, basically I give you some background about runtime power management, especially Linux, Android, and then I'll talk the problems in today's architecture, runtime power management, and last try to present the design, the work we have worked on this. Now, this is perhaps a little bit scary to computer science students. This is you take the phone's chip, you look at the diagram of the chip, the system on chip. This is a BDM transistor, over a BDM transistors. There are a lot of modules on this chip, right? And what you typically a programmer care about is this part. Is a dual core. This example is a dual core Cortex A9 processors. You have Linux on top of it. But on the same chip, you have maybe tens or maybe 100 other modules, I/O controllers, DSP, GPU, face detection, IC, any other actuators, speech codec, things like that, right? These are things that you don't usually care about. You don't usually hear about them, right? And the vendor try to hide them behind the program interface. There are a lot of modules, and if you look at the die photo, this is the same chip, is a die photo. The Cortex A9 cores is only a tiny part of the chip. The rest of them are hidden from the operating system, Palo operating system. And this, the runtime power management care about, right? When your phone is on, you're doing something useful. This guy, the CPU OS is on, like checking the email, running network stack, or doing computation, whatever. The rest of them, you need to put the idle one to sleep. Otherwise, they burn out the power consumption, right? So I hope these two diagrams show you how important runtime power management is, because these modules, this idle module could account for a lot of chip area, a lot of power consumption if you don't put them to sleep timely, right? Now, the module we just talked about is basic unit for power management, right? The smallest entity on a chip that you, in software, you can say, go to sleep or wake up, right? So software define two modes. One is disabled or enabled. Really, that means by enabled, that means that module is running, its context, its register, the content of its register are valuable. You cannot just turn it off, right? When it's enabled, the software essentially telling the hardware, hey, don't turn it off because the context in the registers are meaningful. But in the disabled mode, software mode, that means software basically, I have saved the context for this module. Therefore, it's safe to turn it off completely, and it's not doing anything useful. So this is a software mode, right? In hardware, of course, there are more states, right? The hardware could stop the clock to a module. That's called clock gated, right? So in that state, the context state is retained, right? But there is no clock, no switching, the power consumption reduced. If you want to reduce more power consumption, you have to gate the power. You have shut down the power supply to that module completely. That's called power gated, right? And in that case, your context lost, right? When you resupply the power to the module, you have to restore the context for it to be functional. Okay, so this hopefully explain the behavior of a module, system-on-chip module, when you're doing power management. Now, the modules are organized into domains, right? It's not every module you can individually shut down. Clock gating is cheap, it's just one gate there, you can stop the clock. So therefore, every module can be individually clock gated. But cut down the power is actually expensive in hardware. Therefore, in the system on chip, you don't have a power switch for every module. What you have is you group a number of them into something called power domains. Right? There are also clock domain, for example. Like the multiple module basically getting grouped in the clock domain, but for the entire domain, the clock, hardware for clock generation can be cut off. Right? For power, more of the clock domains can make up a power domain that you can cut down the power consumption for power domain completely. Right? So it's a hierarchical organization. And you cannot fine-grain to basically just turn off one module because it's a hardware cost there to switch on and off. You do it for power domain. Okay? This is hardware backbone. Now, runtime power management essentially is a collaboration between software and hardware. Right? Essentially here is one power domain example. You have I2C controller and it's not being used. The software figured out this guy is idle, right? Therefore, I disable it. That means the software save its context into the memory and basically indicate the hardware to say, no, hardware, it's safe for you to do locate its clock, shut down its power, right? And software could trigger other modules. When all the module of a domain is disabled, the hardware can trigger to shut down the entire clock domain, right? When all of the clock domain within a power domain are gated, the hardware will then decide this power domain, the power supply to the power domain can be cut down. Now this hierarchical organization introduces an interesting problem, right? Even if you have one, this I2C controller's power consumption is very small, it's like 0.1 milliwatt. But the fact, if you fail to disable it, you leave it on, you end up keep everybody in this domain on, right? Let's have a magnifying effect, right? It's like one like college student failed to sleep, basically keep everybody in the door and wake up, right? So that's a lot of waste. Now, software has three responsibility in this process. Number one, you have to decide when to disable or enable a module. You have to decide whether this module is idle or has pending tasks. If there's no pending tasks, I can disable you. Or if you have pending tasks, I should let you keep on working. The second is, once I decide it's time to disable you, I should suspend the module by saving its execution context. Right? If I want to wake you up, enable you, I have to restore the saved context. That's also software responsibility. And finally, the software also has to set what is the final hardware state the module can go into. For example, you don't, if the user really, the application really needs one module to be respond in 1 millisecond, you don't want to put that module into a very low power state that will have 2 millisecond wake up time. Right? Software have to set that target hardware state for the hardware, and hardware will carry out this thing automatically. Okay. Now, on Linux, and most of today's Unix like operating system, iOS, and even Windows Phone, I have to say, the software essentially rely on drivers to do these three things. Right? To decide when to disable enable module, Linux have this thing called runtime power management framework. Right? It's a soft framework, and then you use driver, the collaboration between driver to make the decision. And save and restore exit context is drivers provided routines. Suspend, resume, right? And for the last question, the last task is Linux provide this PMQ, quality of service framework, that allow an application to set a QoS requirement. See, I can only tolerate 2 millisecond latency, and then the hardware will figure out, driver will figure out, okay, according to the data sheet, according to my knowledge of the driver, these following states will meet this requirement. Therefore, these are states that I can potentially put the module. Right? It's really complicated.
For a clock domain, can I modulate it to some intermediate frequency if my load is not that high or it's not that low?
You're talking about frequency scaling, voltage frequency scaling. It's a different thing. So here we're talking idle, when it's not doing anything. You're talking when it is actually doing something, I try to make the doing it slower, right? Therefore, with higher energy efficiency. That's frequency scaling. It's a different mechanism.
Is it possible in mobile?
It's possible. Your device activated this, your CPU frequency, clock frequency changed like 10 times range in real time. All right. Okay, that's all the background. Sorry it takes so long. But now, I think in the work, really, we focus on the first row, right? Decide when to disable, enable the module. How can software infer this to decide? Now it's time. This module is not, it has no pending task. I should suspend your state so that you can go to sleep, right? When it's looking to this. Linux is, again, more detail about Linux. Linux has this thing called runtime framework, which is shown here. And the framework provides a reference counting mechanism for each of the modules, right? So every module, how the module, the framework has a counter there. The counter indicates how many pending tasks this module has. So the drivers is responsible for calling this API provided by this framework so that to increase the counter or decrease the counter. Okay? Drivers are responsible for calling these APIs. And the framework then, when the counter transits from 1 to 0, the framework will decide, okay, that means this module has no pending task. I should suspend it. Therefore, it calls the routine provided by the driver to save the context and disable the module. And likewise, when the transit from 0 to 1, you wake it up and you restore the frameworks, right? And the driver's role, driver's responsibility here is very important. The driver actually is supposed to call this API provided by the Linux runtime PM, which is runtime PM get, right before accessing the module. For example, the driver developer has to call this function in a place before it will do something with the hardware. And it's supposed to call the runtime PM put right after you finish your module. Right? If the driver do this correctly, properly, hunky-dory, everything will be good. The module will be suspended when it's idle. Okay. This is in theory. This is the current Linux runtime power management framework, how it works. Now let's recap. Essentially, the system on chip power management runtime PM is driver will decide when to enable and disable a module, and it will use a QoS requirement to decide what's the target state for the module to enter. And essentially, you infer the driver provide knowledge whether the module has a pending task. When there's no pending task, I'll suspend it. If you have a pending task, make sure you're enabled. Right? Okay. Now this will get a problem. It's a beautiful design. It's emergent. I think it's in the mainstream Linux, I think, since last year. Right? But the problem is, we started looking at this, basically, Chao, the grad student who leads this project, looking to drivers, read all the code, and come back, hey, this driver don't implement any power management. They don't even call this runtime PM get or put, right? That's kind of surprising to us. Mobile phones, every milliwatt matters. Why do you leave them on, right? So we actually, then we looked at OMAP 4. We thought maybe TI driver developers are particularly lousy, right? So we went to Samsung's, went to NVIDIA's, right? We found the problem is ubiquitous, right? It's like for most of them, a lot of the modules the drivers don't have runtime power management support. And sometimes they will be fixed by a patch, but that's like 2 years or 1.5 year after the release. I mean, you know the lifetime of your phone, right? It's like 1 or 2 years. Basically, during your practical useful lifetime of your phone, these modules are left out. You're basically wasting a few hours of standby time every day because of this. So the reason is they don't pretty much care. Drivers, the TI, the drivers are provided by the chip vendor, which is a silicon company, hardware company. They hire a lot of software engineers to write the drivers, right? And they have this tremendous pressure to get this released to market, to get this ready, because the Nokia or Samsung or Apple is not having pressure on me to get this ready. So but what they care, the boss can test its functionality. Is your driver function, is this module would work? You have this I/O controller, does it actually work? Right? Power management is something like almost like gas efficiency. You first care about your cars and actually are safe, you can drive, right? Then you care about gas efficiency. So it's almost afterthought. And then sometimes when they actually care, they don't implement correctly. For example, this is an example. The GPIO is a really simple hardware module. The drivers implement the ideal fine-grained runtime PM would be every time you start doing something to the driver, you call runtime get, and then when you're done, you release it. You do this every time. But the driver just lazy. They're lazy. What they do is whenever you initialize the driver, the device, you basically enable it, and you disable it only when you suspend the whole system, right? So it's left on all the time when you're using the phone. Basically this is evidence that they do know the existence of runtime power management framework. They did use these APIs, but they're just too lazy to do it properly, right?
Quick question. I mean, doesn't all these system calls incur cost too? You know, you're making get, put, every little thing that you do, get, put.
It's very small. It's a counter. It's essentially you increase the counter, decrease the counter. It's a procedure call in the kernel. You call into the runtime
So
part.
does the driver actually run inside the kernel?
Right, driver in the kernel. Right.
Is in the address space of the kernel?
Is in the kernel. Yes.
Okay, so there's really just directly access to the counter.
Right. It's
No
it's API. You basically
context
call
switch?
no
Is there
context switch. No context switch in the kernel. Right. It's very efficient. That's not a big deal. I mean, CPU even you're using like sometimes CPU is fine. Now, actually, we feel sympathy to the driver developers because some of the drivers is very complicated. For example, I basically asked the Chao and Xiaozhu, why don't you try to fix this driver yourself? Right? They took the display controller driver, which has like 22,000 lines of code, have many execution paths, many entry points, and they spent like about 1 month. They couldn't get it done. Right? So if you're not a driver developer, and if you try to fix the problem, it's almost impossible. So the display controller on OMAP 4, which is used on Google Glass and the Galaxy Nexus, basic display controller is always on. Even if your screen is idle, you're looking at the screen, reading newspaper, email, the display controller should be put in sleep, but it's on. Right? Simply because it's too hard for the driver developer to figure out correctly where to call the PM, runtime PM get and runtime PM put.
There may be some also other considerations, such as non-technical, like selling consideration or something like that. Maybe some users would like to have the screen display always on. Or
Right, the
something
display
like
is
that.
up.
So there are some
The
things.
display is up. The display controller should be off. The controller need to be busy only if you update the screen. We're not updating the screen. The display controller is not doing anything. It should be put in sleep. Actually, we fix that. We actually put in sleep. Right. So it's any module that's idle should be put in sleep. That's runtime power management. What I'm showing is because of failure of drivers, they're not put in sleep. Right. That's about 10 milliwatts power consumption. And the thing is a little bit interesting here because nobody can be called responsible for this power drain. Because they will say, hey, I didn't do power management because it only consumed 0.1 milliwatt power. Right, for example, the GPIO. But in reality, because that failure, the entire domain is kept on, that's 17 milliwatt. So that's the psychology of the driver developer is at play here, right? They're basically says, my contribution to power waste is very little, but they forgot that they actually kept the whole domain.
But what I ask is more general. Is this amount of power waste, is it necessarily bad? I mean, maybe there are other considerations that are less technical that can come into play here.
There's, for example, like what?
I don't know if I can just maybe think of an extreme suggestion of just later bug fixing. You know that sometimes you put some when you come up with a product, you make it intentionally not fix, or after that you can fix it and you can upgrade.
Oh, you're
just
saying,
an
I see,
example.
okay.
Yes, I'm thinking
You're saying
about-
we start with a lousy product, then we improve it over next soft release.
It's a selling technique.
You should ask the marketing people, and I don't know, right? So I think it's a different good strategy for grad students, right? The first project you do it lousily, so your advisor will only have praise for you next time.
question is, does changing the state of display controller affect the response time?
No, it won't. It won't. Right. The context restore and save like take microseconds.
So user cannot say anything.
Right. You wouldn't see any difference. Okay.
So just want to play devil's advocate here, right? So, you know, phone, you're talking about phones.
Right.
You know, manufacturer of phones have a target, you know, they want the phone to last, you know, maybe 24 hours
Right.
before recharge. Battery is like 3,000 milliwatt
Right, right.
these days. So you can do a battle calculation,
Right.
you know, that
You have a
you know,
point.
they can meet the
Right. Right.
without
You have a
doing
point.
anything smart.
You have a point, yes. So that's my theory. Energy efficiency is not a good research topic. I mean, I'm shooting at myself, right? Because no matter how efficient make systems are, they will figure out a way to make it just 12 hours battery lifetime, right? So this is exactly the same. Yes, I agree, absolutely agree. So energy efficiency is like, there's no end to it, right? You make it more efficient, they'll figure out a way to use it, the battery. Right here is exactly the same, right? Because their phones, unless their battery lifetime goes beyond like 9 hours a day, then they're getting into trouble, right?
I'm just saying, you know, they were able to get away with this very
Yes,
bad
yes,
quality
yes,
software.
yes.
And still stay within their
Right,
target. you
but
know.
the thing is, when you're going to high end, we'll talk about that. Then it'll make a difference, right? For example, Apple, their battery life is way much better because they do this carefully, right? Then they can sell the premium. You can see because it's 3 hours standby lifetime, Apple can sell this phone to you $10 more, right? And without doing any change to the hardware.
Except the battery is not replaceable.
Right. Yes. All right. So then we get back to an individual device driver developer say, hey, my module can consume like 100 microwatts of power consumption. Why should I care about it, right? And it's to make sure the car can drive safely, right? But the thing is, because you keep the entire clock domain up, and then you keep the entire power domain up. This is the example of OMAP 4, right? The GPIO controller's driver doesn't have power management. Essentially end up costing 40 milliwatts power consumption, additional power consumption. When your phone you're doing something with it, right? So now we have identified the problem, right? So this 17 milliwatts is not allowed for Google Glass type of device because your battery is so small, right? The problem clear because drivers suck, right? Driver developers suck, right? Solution one. This is essentially Apple did, right? Just hire more and better developers to make sure your driver are correct. You do all the power management correctly, right? The student who did this work interviewed Apple, got an offer. When he come back and said, he talked about his work at Apple, he said, Apple people to me, they don't need our work because they just make sure they have good driver developers, right? So, but that's not the case by Android people. Right, Samsung or even let's say Huawei or Xiaomi. I mean, I hope they have the financial resource how better. So then the next solution is my student immediate reaction to say, hey, let's build a tool, right? If the driver developer have problem do this, build a tool that you can run through drivers. I can insert code automatically into a driver to do runtime power management. We actually did this, right? It's a part, we call it Power Advisor. Essentially, you instrument your driver, you collect some runtime traces, and there's a essentially become linear optimization problem. You can solve the problem, you figure out where to insert them. There's no guarantee of correctness, but at least help the driver developer to insert needle in the haystack. Right? But the thing is, for me, that doesn't bring the intellectual satisfaction. Right? Building a tool, it's nice, but I mean, you become bug fixer, right? I want to do more. So basically, this come from my very many years of my kind of principle is the human have bounded rationality. We are essentially stupid, right? So let's say instead of trying to fix bugs, let's try to design the system so that it's impossible for people to find bugs, right? If we cannot change the developer, why don't we change the system? Right? So basically pinpoint to the, hey, maybe Linux runtime power management framework is the one to blame. Can we redesign it so that we actually don't need driver developer to get involved? So that become the solution I'm going to talk about. Because centralized runtime power management. Because today's Linux, each driver has to be responsible for its modules power management. And the solution we have, essentially you have a central module in the kernel that does power management for every modules. Right? Okay, that's centralized. So essentially the key insight comes from understanding what's the fundamental information you need to do runtime power management. Number one is you need to know what is the application's latency requirement. For example, how fast you need the module to wake up, right? And number two, you need to know the wake up latency for that particular module when you come out from a certain state, right? Number three is you need to know whether the module has pending tasks. Epiphany comes. The first two are basically the number one is application can express its requirements through the QoS framework. Number two is datasheet. Is it datasheet? Right? The hardware vendor, you know the number, the latency. Essentially, why you need drivers because it's not specific information. Whether a module has pending task. That's essential information today's drivers supposed to supply to the runtime power management framework. Right? And our epiphany is this information can be inferred outside the device driver without device driver providing information. Okay. And I'm going to show you how briefly. Now, on the left is Linux today's runtime power management framework. You rely on this reference counting, right? This guy does reference counting, and the driver have to call the API properly so that the reference counter is maintained properly. What we propose is, and of course then you have this routine provided by driver that's going to save the states and resume state of the device, right? What we propose is basic driver don't need to do responsible reference counting anymore, right? Driver only provide the routines to suspend and resume a module. That's it, which is static information. And then we replace the runtime frame power management with a monitor and a controller, the central power management agent. And I will elaborate on that. Okay, how can we do this? How can we infer whether a module has pending task without driver providing information? So in this case, the driver only provides a mechanism, which is the power management routine, suspend, resume, and central power management agent decided when to call which routine, whether to suspend or resume. That's the responsibility of this module, the central power management agent. Driver is no longer responsible for that decision. Now, first of all, let's talk about the software solution. Of course, software solution is free, right? You don't have to modify the hardware, just modify the software. The software solution is basically with observation. If you look to system on chip modules, if there is a pending task, if there's something going to task to that module, for example, I2C controller or GPU, then you would see there will be its register sitting on the bus would have access. There's someone is going to send in register read and write to that module if there's a pending task. Because once you have pending task, you don't withhold it. You will send it as soon as possible out, right? So that's the observation. So with that observation, then you could have a hypothesis. When there are low register access for a period of time, that means this module should have no pending task, right? So the problem reduced to infer whether the module has pending task to monitor the register access of the module. If there's no register access for a period of time, we declare this guy had no pending task, and therefore it's safe to suspend it, put into the no power state. And this is an example. For example, this is CPU runs the I2C driver, this time access from that, and you have this I2C controller. When the CPU has tasks for this I2C controller, you will see frequent access to registers to this I2C controller. It's program interface with the registers. And likely on all ARM-based SoCs, all the peripheral devices modules, their registers are memory mapped. Therefore, it's easy to monitor its access. Basically, just use the memory protection mechanism. Right? What we end up doing is we periodically remove the access permission for the registers, or the module we care about, right? And then, if there is access to the module that generates memory exception, then we know, okay, that module is accessed during this period of time. Right? At that moment, we remove the protection to let the following access go through without sacrifice performance. And then when the next periodic check comes in, we remove we enforce protection mechanism again. So by this, we can infer during the past period of time, the T threshold, whether the module has been accessed. Right? I'll use an example to show this. Right? So this is enabled module, and periodically we remove the read-write permission. Right? So that means if the first register access come from, we generate memory exception, and then we take note, okay, this guy got access during this period, and then we remove the protection, so that the following register access will go through without overhead. And then when the next periodical check coming, the next, this one, here, you will know this module has been accessed in the past period, therefore it's not idle, there's pending task, it's don't do anything. Now, then you move forward, during this period of time, there's no register access. At this point, you will know, okay, this module hasn't been accessed in the past period. Therefore, there's no pending task, which is suspended. Okay, it's very simple idea. Okay. So actually implement this OMAP 4 based development kit for the Panda board with the Naranix, and we showed the test module essentially looking into the MMC controller. Is used by the file system on the secure digital card. And the I2C SDIO controllers, these are used by Wi-Fi interface. And the display controller. And we collect the usage trace so that we can basically replay the activity, repeat the experiments. What we found, central power management is equally effective as good drivers. For example, in this case, the MNC driver, I2C driver, they actually come with good implementation of runtime power management. So our central agent basically can put about this gray one is the percentage of time the module is disabled. Right? It's very close to the stop limit driver. Okay. On the other hand, we enable runtime power management for bad drivers. In this case, it's SDIO controller, display controller. Right? They don't have any power management code in there, but our central power management can disable them for like about 80% of time. Right? Which is turning to extend the standby time for a smartphone by 3 hours. And this number, of course, is being larger if you look at the wearables like phone and watch, right? Because the battery is smaller, because we save about 10 milliwatts of power consumption, 17 milliwatts of power consumption. It's translated into longer battery lifetime save on smaller devices. Now, to recap, essentially, the central power management architecture, we basically develop driver from doing power management, and it's comparable with hand-tuned power management, and it has no hardware modification, right, which is nice. But it does not work for all SoC modules because the assumption we made. The assumption is when there is no register access in the past period of time, there is no activities, right? So this threshold in our experiments is 100 milliseconds because we observed for most I/O devices, the transaction any processing of the transaction take much less than 100 milliseconds, except for DSP and GPU. This computational device, you can give them a very heavy computer task. They can keep doing the job. And from outside, you will see there's no register access for arbitrary long period of time, depending on how you program it. So therefore, this software solution wouldn't work for these programmable devices, right? And of course, and also because the period is bounded, 100 milliseconds bounded by the longest time, the shortest time a transaction would take. Therefore, within the threshold, you cannot do fine-grained power management. For example, the device has to be left on if you're idle for 100 milliseconds. You cannot shut it down between them. So it's not extremely efficient.
Even for I/O devices, isn't it possible that the device is waiting for some external input and then you think that it's...
Usually on the system on chip, waiting is done by interrupt event driven. So you're not polling. So the controller would go to sleep and they will have a wake up mechanism to wake up from outside. So in that case, it's still safe to suspend it. Okay. Now the key problem here is it wouldn't work. Is software doesn't know whether a module is busy or idle. Sounds ridiculous, right? You have software running on a system on chip, you don't even know, have no firm evidence whether a particular device on the system on chip is idle or not. right? So that's why our software-only solution spend all this memory protection and register access monitor trying to figure out if modules idle or not. So that moment, that reminds me of a joke told by Moshe. I don't know if you guys heard about it. I mean, Linda, you probably heard it. It's when Keith was giving a talk about the PACE project, the compiler figure out microarchitecture project. So Moshe is asked a question, say, your research reminds me of a joke. Basically, a guy went to the dentist, say, I got a back tooth. Okay, he opens his mouth, and the dentist look inside, look, and then ask that guy to say, hey, tell me which tooth hurt. The guy responds, you are the dentist, you tell me. So, in this case, the hardware is the guy with the bad tooth, and the dentist is the software, right? Essentially, why doesn't just the hardware tell us whether it's busy or idle, right? Why we're spending all the time, energy, software looking inside to figure it out, right? So that leads to the next step, to say, hey, why don't we modify the hardware a little bit so that we just provide one bit information to indicate whether the module is actually idle or not. That basically solves all the problem. All this software fuss is gone. You don't need any more. What you just need to do is add a bit of information and the central power management agent just pull that bit theoretically. But that period could be very fast. It could be like 1 millisecond. Every 1 millisecond you pull that to see if it's idle. That makes the power management way much more fine-grained, and it would work for every device, including GPU and DSP. The more important thing, if you know how to work, you will know how to often already have this bit there. It's just in today's SOC, they don't export this bit information out to the software asset. So, I mean, it's basically we're telling TI or Qualcomm, please modify the hardware a little bit, it will simplify the software guy's job, please, right? So, we actually, again, we prototype, we take this Xilinx Zinc board, it's a system on chip, but they have a huge FPGA there. Right? You have dual-core ARM processor here, we put Linux on top, runtime power management on top. We basically take this FPGA, we take the Xilinx I2C controller, DPI controller IP, we modify it so that they export that bit information so that we see if we can actually do it. I mean, it's no surprise, it just work, right? It's easy. So the hardware modification is very small. As I said, the hardware often already have this information, but it's idle now. If you know the hardware IP, it's essentially a finite state machine. But when it's idle, that means it's in certain states. What you need to do is just pull a while from each of the states and or AND gates, some small gates there, you pull that information out. Right? So here we show it's a few extra gates. If you don't already have that bit information, you add a few extra gates, you can get the information. And if you look at the code, this is for science people, if you look at Verilog code, it's just a few lines of code. There's a Verilog code, it's very simple. Basically, we modify the I2C controller's code to export that bit information. Okay. Now to recap, again, so with central power management, we can relieve drivers from doing power management and just enable aggressive power management. There is very little overhead, you don't need memory protection at all, and it works for all modules. If that module provides that one bit of information, whether it's idle or not. Okay? Now, the final work is, this is original, the next runtime power management, with driver play a big role. Right now, what we have is a central power management agent that works for all modules. Right? The device driver only provides the power management routine to suspend and resume a module. And this central agent decides when to do it. Right. Now, moving forward, it's not end of story. What we're doing now is today's runtime power management on the powerful CPU. Because on the usage model on your phone, when you press a button, your CPU is wake up, is doing work for you. But on the emergent services, like your wearables, your glass, your watch, even your phone these days, a lot of the access actually come from a very low power core. Your CPU is sleeping. Your CPU is actually not doing anything, but you have a very efficient microcontroller core that serves all the background activities. And that means you need to do runtime power management from here, because this guy's sleeping, right? With today's architecture, you cannot do it because to move to the low power core, you have to move all the drivers to the low power core, which is extraordinarily hard because the power is not powerful enough, right? with our centralized architecture, it actually become easier, right? You can actually, first step, you can pull the monitor here. So that the polling the Rexer bit or monitor the memory access can be done from low power core with the CPU sleeping. Only you realize I need to suspend or resume a device, you call the controller to invoke the driver's APIs to do it, right? One step further, you could have the whole central power management in low power core. But you need to pull this suspend and resume routines from the driver to the power core, and you have to provide the BSM for the state consistency. Right? Even further, you could completely get rid of, you rethink about driver's role. Even you see the routines for suspend and resume the states should not be part of the driver responsibility. A central module should do it. This is something we're working on today. Now, in summary, I hope I convinced you driver-directed power management is harmful. Centralized architecture equally effective, and a little bit of hardware modification can go a long way. So if you're interested in this code, you go to our webpage and check it out. Actually, this is ASCOS paper this year. But since this is a grad student talk, I like this project. It's not because it's a very significant work. It's actually have many moral. I used to tell my grad students how to do research, even it's not that. Okay, sorry for interruption. So there are a few lessons from this project I want to share with grad students. Number one is there's no $10 bill. So you guys heard about the joke, two economists working on the street. You want to tell the other, there's a $10 bill on the other side of the street, right? And then economics would say, no, if it were, someone else would pick it up, right? So this goes to how we identify this problem, right? So we are able to publish paper, work on this, simply because runtime power management is a new thing. It's just become the mainstream last year. And that's the same time we started working on it, right? So that means if you want to see $10 bill on the street, you better walk on the street that very few people have been working on, right? That's a chance you are the first ones that $10 bill is higher. At the same time, if the project you work on is a low-hanging fruit, you should really work hard to get it quick, because other people may pick it up if you don't do it quick, right? So no $10 bill, free $10 bill. The second one is, I think, really important, is think like architect, right? So tools are nice, but I think the designs are even nicer. Right? Like the student, the child first came to me to say, hey, there's a problem, let's build a bug fixing tool, fix it. That's the thinking of being a tool, right? Build a tool, being a bug fixer. I think if you take look at the problem deeper, think about whether the design could be fundamentally different to avoid this bug and make the problem more interesting. So think like architect, not just as a tool builder. But another one is get out of the comfort zone. So even if you're a computer science major, right, you should feel free to modify hardware, right? Even if you're an architect, if it's necessary for you to do plumbing, you should do the plumbing. You should learn how to do a tool, right? So get out of the comfort zone. If you have to modify the hardware, modify it. That's one thing. Another thing we learn from this, right? If you actually modify the hardware, the problem becomes much simpler. Solution becomes much simpler. The last one is really important. You can tell from, this is a small problem, actually small problem, but you can say, somehow I felt it's a lice problem because I have layers, right? You identify a problem, you can quickly throw a tool to fix the bug. Then an advisor tell you, hey, tool is not enough, think of design. You go back, find the software design. The advisor tells you, hey, software design has limitations. Then try to fix the hardware. Then you basically have layers. You can provide one solution, a limitation, you go one layer deeper, right? Just like wines, movies, right? Good stories all have layers. Good research problems also have layers. So that's basically the moral of the story. It's not the most proud work I've done, but I think it's nice to share because it kind of show what type of work we do in our group. And this is some small lesson we can learn from doing this research. Okay, thank you.
Thank you, Dr. Song, for the talk and the exciting grad school. Now, let's open the floor for questions.
From from your talk, I assume that every module has different idle mode, right? And different idle mode has different wait of time. So how do I decide which idle mode I should send the module to?
That's the Linux runtime QoS framework. Right, the application expressed its requirement by calling an API provided by framework. And the driver basically, according to that, driver will indicate the following states are locked for most of the requirement. That's done by the Linux runtime QoS framework.
So yes, this is a question more just for someone who's interested in saving power. So there's an obvious relationship between time complexity of an algorithm and the cost of power, right? So if you have more steps, you've got like a very expensive algorithm, it's going to cost power to compute. Whereas if you have a more efficient way to do it from like a time complexity standpoint, it's going to cost less power. But sort of built into the building blocks of complexity analysis is this idea that there's a concept of steps, and these steps are sort of equal. But I suspect that at the layer you live, even deeper, like this is actually not true. That certain types of operations have different impact on the utilization of power. So does it make sense for us to sort of increase the resolution? If we're interested in about power, does it make sense for us to increase our resolution of understanding of the step and break that down into different components and then start labeling algorithms in terms of their power requirements, like a power complexity? Is this a good idea? Should we be doing this?
You're already, it's very nice. I'm glad you're thinking this way. Now you're kind of thinking like computer engineering, right? You no longer look at the algorithm to say there's a line of code, right? You're thinking about what's the hardware units behind executing that instruction. So you're thinking like computer engineer. You're thinking like a hardware architect already. So that's what people do. So they're actually, one of the very first software energy efficient paper is done by someone from Princeton, harmonic student. He basically take a multimeter, measure the energy consumption for each of the x86 instructions. Basically provide a table to say this is how many joules each instruction costs, right? And using that, then you can use that to optimize, use a compiler to optimize the compilation. You use the more efficient instruction more often, right? So people have certainly explored this direction before.
So what's the one piece of advice that you would give to a software engineer who is afraid of the hardware, wants to push it far away? How should I think differently about
I would say that right now I would say it's because compiler people and hardware people have done such a good job. There's not much juice you can squeeze out of the real execution efficiency, right? The problem these days, I think, from the energy efficiency community, low power design community, is how do you do idle better? How do you do nothing better? Like for data center, for base stations, for example, most of the time the idle utilization is like 15–20%, right? How could you make sure when it's idle, not doing anything, you scale it down, shut down its power consumption? So that's this work essentially touch on very small scale, this is on chip scale by this problem, right? That's to summarize, execution efficiency, I believe, there's not much room you can improve, but most interesting problem comes from idle time. You're not doing anything. How could you make it lower power?
So going back to your answer to the first question, the software is responsible for saying what its requirements are of the hardware, and the whole premise of this talk is that the people writing the driver software do a very poor job of managing power, so it follows that the people writing the applications aren't necessarily going to give accurate descriptions of what they need. So this sounds like it's adding another layer on top of your problem, and I was here last week when Dan talked with some of his students. I've talked before about for security permissions in Android applications, a lot of them request way more than they actually need just because the developer is lazy. So do you see that as an issue?
This is not addition layer abstraction, first of all, right? Essentially, it's about who does what. Basically, we're saying driver, you should not be responsible for maintaining the reference country, right? We have another module that does it for every module, right? And I think right now the driver is a big mess because it violates a very important rule in computer system design. If you guys read the Art of Unix Programming, I highly recommend this book if you're interested in system. Just read the first chapter. It summarizes about 20–30 rules when you build a large software system. One rule, my favorite rule today and recently, is a rule of repetition. That is, you should put knowledge in data structure and don't put the logic. Today, the driver essentially is a big logic with all the knowledge inside. The driver developer are from the hardware vendors. They're supposed to know the latency of wake up time. They're supposed to know when the device will wake up, when it's happening task or not, right? So driver developer code a lot of this knowledge into the drivers. And that's the problem. What we're arguing, this line work essentially that knowledge should be pulled out into data structure. Therefore, driver doesn't need to deal with them. Another kernel module, centralized module could do this for all the drivers. The same principle has already been applied in Linux. For example, how many of you know device tree? Device tree? The bootloader. How many of you have ever looked at the bootloader of a computer? Right? When you, in the past, every board, every computer you have a dedicated bootloader. Because that bootloader is like the driver, have all the knowledge inside about where to find an I/O device. Right? That creates a big mess in the ARM-based system. Because there's so many different boards, so many systems out there, every system developer have to provide bootloader. Right? Essentially the same here. But today what they do is the system builder vendor just put all the knowledge into a data structure called device tree. And then there's the bootloader, the standard bootloader will read this device tree and bootload their system. So here we're doing essentially the same thing, to take the knowledge out of the driver, so that the knowledge can be used by a central module that can be audited easily to perform the task. So philosophically, I think the centralized architecture is more secure. At least easy to attest, to prove it's secure. Right? Because it's only a single location, single piece of code you look into. Instead of a driver, then you have to audit every driver to make sure the runtime environment is done properly.
So I believe the original abstraction of this driver was made to, like, since we don't know what kind of devices we will be adding, so let's keep the power management to the driver so that they decide, to the driver so that they decide it.
Right, driver today does a lot of things, because I think here it goes back, now we're going back 50 years in computer's history, right? In the 50 years ago, computer is CPU and memory, right? You don't have many sensors, you don't have many I/Os. That supercomputer is a microprocessor you deal with. So therefore, the operating system is very mature in handling memory and CPU, I/O, right? I/O devices it's kind of afterthought. Okay, it's not part of OS. Let's do driver. Write the driver. The driver has all the knowledge about where to find the device, which direction to write, and how to interpret the I/O control out of system code. Right? So that's exactly the problem. The driver code has a lot of knowledge that should have been pulled out, put in data structure. And they're already doing this for other part of the operating system, the bootloader. Right? Bootloader, you can think about the first driver for the whole system that basically tells the operating system where to find each device, how to initialize it. Right? So I think driver is a big pain in the ass for software systems. And because you dumped all the messy stuff in the driver. And while in the rest of the system, scheduler, virtual memory, they're so beautiful. Right? If you look to actually standard operating system textbook, the scheduler and virtual memory textbook, the part is very elegant. And there's no chapter about the I/O drivers, right? Because that's a messy part. Right? And every driver is different, every I/O is different. It's basically anything we cannot cover in the scheduler or virtual memory is part of the driver. Right? Okay.
So, I think the centralized power management would possibly require modifying the kernel, right?
Right. It's
So
a kernel
instead of
module.
that, would it be possible to have an app that sort of spies on all these devices and calls the power management on their behalf, so that for devices where you can't modify the kernel, you have some other power management system?
Unfortunately, you have to modify the kernel, right? Because there's certain information only available in the kernel. Unless you want to export new system code. New system code is monitor that bit, right? Then you still need to write the kernel module to implement system code, right? So you need to have to do something in the kernel. Right? Maybe the central power management, the policy may live in the user space, but the mechanism to check the information, gather information, have to be in the kernel.
So you're saying for the power switches, because of the power switches, the domains are divided into power domains
Right.
and further down to clock domains. In your
Right.
research, have you seen cases in which certain clock domains keeps blocking others from, keeps the power domain from switched off?
Right, that's exactly GPIO case.
Yeah,
The
but
G-
even with the improvement,
Oh, with the improvement, then they will go through, they will be part of,
They'll
right,
all
right,
go through.
we'll be able, the whole power domain will be disabled.
okay, I see.
That's the point, that's we solve the problem, right?
Yeah, it just seems like if they have different power usage behaviors, it's much less likely they will all be idle at the same time, and therefore you cannot switch off the whole power domain.
So I think when the group decide which module to put in the domain, they actually consider these factors. Often these two module are in one domain is because the function of one module require the other one to be up.
Yeah.
So they already figured this out. The hardware developer, they have this intelligence here to do this.
Unfortunately, due to time constraints, we'll have to end it up here. We can take more questions offline. Let's thank Dr. Song once again. So, two important announcements. Next week, we'll not have a code of talk. Instead, there's a K2I distinguished speaker talk, so please go there. And grad students, remember to sign the sheet before the meeting. Thank you.
Right, because lower level typically. Right. We're the plumbers. Go to fixing the leaks in the line. The one without format is has secrets. When you between that and GPIO case, it gives you something. It's just they don't do it properly. Most times, right? So I have to say, as I said, this is not the most this is the biggest deal of research ever. I think that it shows what's a pipe for fixing, right? Which type of problem where. So in reality, I think the example is good driver developers make sure they will not get a bonus if they don't improve power management and problem fix, right? But intellectually, I think it's interesting because that made us to question the driver. So basically, the follow-up of this project was really essential to think about why do we need driver? Maybe every device vendor should just provide a data structure for that device. I have some things, universal driver that does the function for everything. Just put knowledge in the structure. It's like device. So it's like slowly layer up layer, right? So this we still have layers to explore this process.
So, I don't think that I answered my question very clearly.
Okay.
Because
Let's do again.